Hello and welcome to the lecture series on the binomial theorem. In the previous lectures, we've seen certain identities based on the binomial coefficients. In this lecture, we will be looking at more identities which the binomial coefficients obey. So recall that the binomial theorem is given as follows: x plus y whole power n is summation r equal to 0 to n cr x power n minus r y power r, where cr denotes ncr. We can also derive the related identity 1 plus x the whole power n equals summation r equal to 0 to n cr x power r, and in the previous lectures we've seen how useful this identity can be in deriving identities based on the binomial coefficients. So in this lecture we will derive further identities of the binomial coefficients, and the first identity is the following. It asks us to show that c0 plus c1 over 2 plus c2 over 3 and so on till cn over n plus 1 equal to 2 power n plus 1 minus 1 whole divided by n plus 1. In the previous lecture, we've seen identities that the binomial coefficients obey, where we have integers multiplying the binomial coefficients, whereas in this lecture we will be primarily concerned with identities where we have fractions of the binomial coefficients obeying certain identities. So we've seen two techniques previously for proving identities based on the binomial coefficients. One was the differentiation technique, and the other was the technique which used binomial identities. In this lecture, we will be looking at an integration technique and a technique which uses binomial identities. So the motivation for that is as follows. Previously, since we had integers multiplying the binomial coefficients, we could derive those results by differentiating the expression 1 plus x to the whole power n suitably, whereas since now we have integers dividing the binomial coefficients, we can integrate this expression so that we have the binomial coefficients divided by certain integers, and we can substitute values of x suitably. So we look at two approaches for proving this identity. And the first approach, which I'll call approach 1, is to use the integration technique. So let's look at 1 plus x to the whole power n equal to summation r goes from 0 to n cr x power r, where once again I remind the viewer that cr is ncr. So we integrate both sides of this expression over x, and we let x run from 0 to 1. So on the left hand side we have integral 0 to 1 plus x to the whole power n dx, and on the right hand side we have integral x goes from 0 to 1 summation r equal to 0 to n cr x power r dx. The left hand side integral is easy to evaluate. This is nothing but 1 plus x to the whole power n plus 1 over n plus 1, and x running between 0 and 1. And in the right hand side we have an integral of a summation, that is an integral of a power series. And so right now we will sweep it under the rug and assume that we can interchange the summation and the integral, and we can integrate each term separately to obtain summation r equal to 0 to n cr x power r plus 1 over r plus 1, and x running between 0 and 1. The left hand side integral comes out to be 2 power n plus 1 over n plus 1 for the upper limit, and minus 1 over n plus 1 for the lower limit. And the right hand side comes out to be summation r equal to 0 to n cr 1 power r plus 1, which is just 1 over r plus 1. Notice that summation cr over r plus 1 is exactly the left hand side of the identity which we want to show, and 2 power n plus 1 minus 1 over n plus 1 is exactly the right hand side of what we want to show. So we've shown the identity to be true using the using the integration technique. Well, as I mentioned, there's a second approach we can take for proving this identity, and that is based on a combinatorial result. So let me call that approach 2. So once again, we would like to derive a closed form expression, summation r equal to 0 to n CR over r plus 1. So the reason why we can't evaluate this summation simply is because we have both the numerator and denominator varying with r. And so we would like to get the dependence of the denominator r. We would like to get rid of the dependence of the denominator with respect to r. And so we'll use an identity which we've seen in the first lecture, which is nothing but summation r equal to 0 to n, where CR over r plus 1 is replaced by n plus 1 CR plus 1 over n plus 1. So this is a result we've seen in our very first lecture on the binomial theorem. And so what this does is now this gets rid of the dependence of the denominator on r, and so we can take the denominator out of the summation. And so this will give us 1 over n plus 1 summation r equal to 0 to n plus 1 CR plus 1. Now notice that the summation looks very similar to the summation of the binomial coefficients, except the indices run from 1 to n plus 1. And so we would just like to transform this to a known summation. So we'll use the change of indices, and we'll run r from 1 to n plus 1. So it'll be n plus 1 CR. Now this is almost the same as the summation of the binomial coefficients. And so we can rewrite that summation as 1 over n plus 1 summation r equal to 0 to n plus 1 n plus 1 CR minus n plus 1 C0, where we are adding and subtracting n plus 1 C0 from this expression. And so that gives us 1 over n plus 1, and we know summation r equal to 0 to n plus 1 CR is just 2 power n plus 1 from a result we've seen in one of the previous lectures, and n plus 1 C0 is nothing but 1. So once again, this gives us summation CR over r plus 1 equals 1 over n plus 1 times 2 power n plus 1 minus 1, which is the result we would like to show here. So to recap, we've seen two different techniques for showing this following binomial identity. One was the integration technique, and the other was a technique which was based on a combinatorial identity, which is CR over r plus 1 equals n plus 1 CR plus 1 over n plus 1. So in general, you could use either of these techniques to show a particular identity on the binomial coefficients where you have fractions, but it might actually be easier for you to use the integration technique, since it's more generally applicable, as we will see in the later examples. So our second example, or our second identity, states the following. It says that C0 minus C1 over 2 plus C2 over 3 and so on till minus 1 power n Cn over n plus 1 equals 1 over n plus 1. So this is our identity. This is the identity we want to show. So notice that this looks very similar to this identity, except we have alternating signs in the summation. So once again, you can use either the integration technique or the combinatorial technique to show this identity. But for this lecture, I will only use the integration technique to show that this is true. So once again, we consider 1 plus x to the whole power n equals summation r equal to 0 to n CR x power r, and we integrate both sides of this expression now between 0 and minus 1. Once again, you can evaluate the integral on the left hand side. This turns out to be 1 plus x to the whole power n plus 1 over n plus 1, evaluated between 0 and minus 1. And the right hand side once again can be evaluated to be summation r equal to 0 to n CR x power r plus 1 over r plus 1 evaluated between 0 and minus 1. So the left hand side evaluates to 0 over n plus 1 minus 1 over n plus 1, and the right hand side evaluates to summation r equal to 0 to n minus 1 power r plus 1 CR over r plus 1. Now you can multiply both sides of this equality with minus 1. That will imply 1 over n plus 1 equals summation r equal to 0 to n. And minus 1 power r plus 2 is nothing but minus 1 power r. Right, this is minus 1 power r CR over r plus 1. And this right hand side is exactly the left hand side of this identity we want to show. And this left hand side is 1 by n plus 1, which is exactly what we want to show. So once again, we've seen using the integration technique that you can derive identities based on binomial coefficients, where the binomial coefficients are weighted by fractions of integers. So we will see yet another identity based on the binomial coefficients next. This identity states that 2 times C naught plus 2 square times C1 over 2 plus 2 cubed times C2 over 3 and so on till 2 power n plus 1 Cn over n plus 1 equals 3 power n plus 1 minus 1 over n plus 1. So this identity seems very similar to the first identity, except now we have the binomial coefficients also being multiplied by powers of 2. So this result is this proof is going to be very similar to the first proof, and I'm just going to illustrate this proof now using approach 2. I'm not going to use the integration approach, but I'm just going to use the combinatorial result to derive this identity. So let's write out the general form of the summation. So this is nothing but summation r equal to 0 to n 2 power r plus 1 CR over r plus 1. So we would like to derive a closed form expression for this summation. So once again, notice that this looks very similar to this, except you have a 2 power r plus 1 multiplying each term. So once again, you can perform this similar trick. You can use the combinatorial identity to obtain summation r equal to 0 to n 2 power r plus 1 n plus 1 C r plus 1 whole divided by n plus 1. So we've just used the combinatorial identity once again, and so this summation is equal to summation 1 over n plus 1 summation r equal to 0 to n plus 1 C r plus 1 times 2 power r plus 1. Now if you compare this summation to the binomial expansion of 1 plus x to the whole power n, where you replace n with n plus 1, before we do that, let's just change the index on the summation. Let's reformulate this to 1 over n plus 1 summation r equal to 1 to r equal to 1 to n plus 1 C r 2 power r plus 1. So this is in a form which is more amenable to comparison. So when you compare this summation to this summation here, where you replace n with n plus 1, you notice that you're missing the r equal to 0 term. But apart from that, you're just replacing I'm sorry, I've got to replace r plus 1 with r even in 2 power r plus 1. So I need to have 2 power r here, since now r is running from 1 to n. So you notice that you have n plus 1 CR, which corresponds to CR here, and instead of x power r, you have 2 power r. So this looks very much like the binomial expansion of 1 plus x the whole power n with x equal to 2, except that it's missing one of the terms. So we're going to use that result and have 1 over n plus 1 times summation r equal to 0 to n plus 1 CR times 2 power r. So we've added an r equal to 0 term, and now we've got to subtract that term from this summation. So that we're going to subtract n plus 1 C0 times 2 power 0. So this first summation, as I mentioned, is can be obtained by substituting x equal to 2 in this in the binomial expansion of 1 plus x to the whole power n plus 1. And so this is going to give us 1 over n plus 1, 1 plus 2 whole power n plus 1, and this last term is just minus 1. So this gives us 1 over n plus 1 times 3 power n plus 1 minus 1, and which is exactly the right hand side of this result. So notice that we've used the combinatorial technique to derive this identity, and we just noticed that the summation we obtained was a modified form of the binomial expansion of 1 plus x to the whole power n, with x being substituted to a suitable value. Whereas in one of the previous examples, we saw x was substituted to be equal to 1 here, whereas now we had x to be substituted to be 2, which gave us this different result in this case. So I leave the following problem as an exercise to the viewer. You should be able to derive this result based on the previous examples we've seen. So exercise. It says, show that summation r equal to 0 to n CR over r plus 1 times r plus 2, this equals 2 power n plus 2 minus n plus 3 whole divided by n plus 1 times n plus 2. So you're asked to show this result. And notice that this result looks very similar to the previous results we've derived. And you can clearly see that you can obtain this result by using the integration technique fairly easily by integrating twice instead of just once, as we've done in the previous examples.